fields like in stress analysis, like finite element analysis. In principle, fundamentally, the CFD and FEA both are same, but there is certain difference, and because of that difference, CFD is generally used for fluid flow and heat transfer analysis, whereas uh, finite element analysis is used for stress analysis. Okay, so that's the basic difference. Okay, before we go into this lesson, I would like to make a small announcement. Uh, the We see you have this. You have a mail last week, I think Thursday or Friday, you had a mail from the Dean and HOD, Dr. Srikanth, announcing about a value-added course, or called as value-added program or value-added course, whatever it is. It is on the topic of exergy analysis in IC engines. So myself and Dr. Firoz Khan are offering that course, and uh, we are taking a maximum of 20 students. It will be offered for a span of 30 hours over the weekends. So part of the course will be before you report to the campus, and remaining will be after you come to the campus. Okay, this will be usually on the weekends, most likely Saturdays. So every Saturday, couple of hours we'll sit together, and you will learn about the exergy analysis in advanced IC engines. So first you will be taught about the advanced IC engines, and then how to perform an exergy analysis, and then exergio-economic analysis. And you will also be made to do some experiments, and finally uh, we will do some work, and will communicate that to for a publication, either for a conference or for a journal. So this is the plan for this value-added program. If anyone of you is interested, you can actually enroll. There is a link there for the Google form there. You can fill it, and will be considered for enrollment. As I said, maximum 20 students. So that's the capacity, and you can benefit from that, if you, especially if you are trying to go for higher education. This kind of work, this kind of exposure will be useful to you. Usually, these value-added programs are those. The content of these programs is such that you'll be covering what is not regularly offered in the syllabus of the mechanical engineering. So, this is something outside the syllabus, but you'll get a certificate, and also there are other benefits, as I told you. So there are 14 students already enrolled. There are 6 more vacancies. If you want, you can enroll that. Okay. So that's about the value-added program. Now let us get back to uh, the, the subject here, heat transfer. So in this class, we'll solve a couple of problems involving semi-infinite solids. So earlier I told you there are 2 more solids. One is the lump system, and another one is the infinite solid. In lump systems, the Biot number is less than 0.1. In infinite solids and the semi-infinite solids, the the Biot number is greater than 0.1. Okay, so for lump systems, we have analytical solution available, so pretty accurate, fine, easy. Whereas for infinite systems, we had an infinite series summation of analytical solution, which can be simplified to one term solution if the Fourier number is greater than 0.2. And if the Fourier number is greater than 0.2, we also have a chart called as the Heisler's charts, and we can also evaluate the heat transfer using what is called as the Grober chart. So that we have seen in the last class. The last type of one-dimensional heat conduction transient system that is in our syllabus is what is called as the semi-infinite body. So the typical nature of a semi-infinite body is something like this. Let me show my screen. I'll share my presentation. So you see here this I have put this points together so that when a problem is posed to you and you understand that is a a transient conduction problem, but you don't know whether it's a lumped or infinite solid or semi-infinite solid, you can use this table to find out, roughly tell whether it's a infinite solid or a semi-infinite solid. So lump systems are usually compact, infinite solids are large, but semi-infinite solids are extremely huge. They are so huge that uh, on one side of the body, if some thermal effect is happening, the other side of the body will not know. So they are so huge. So thermal effects take a very, very long time. The times involved in the semi-infinite solids are extremely large. So, and also in the problem statement, usually the for lump system and semi-infinite solids, some dimension of the object will be given. But for semi-infinite solids, there is no point in giving the dimension of the object. So that is another point or another indicator that it is a semi-infinite solid. There is no dimension given to you so that you can calculate Biot number. You won't, most likely, you won't even be able to calculate the Biot number. So in such a case, you can trust that this is a semi-infinite solid. Okay. So these are some pointers. And also you see in the lump system, we had uh, we had this characteristic dimension in Biot number. Biot number is hx by k, and in that characteristic dimension, I'll write it down here. In lumped, Biot is hx by k. X was defined for slab, for cylinder, and for sphere. You see that slide. You have this equations. Uh, Whereas for infinite solids, you have these three shapes mentioned. So you have charts for slab, cylinder, and sphere. Whereas for semi-infinite solids, there is no shape. There's no shape coming into picture because the objects we are dealing with are extremely large that we consider all of them as flat. You know that Earth is spherical in shape. Earth is spherical in shape, huge sphere. But if you take only a small area, we can treat this as a small length. You can treat it as a flat surface. Likewise, in semi-infinite solids, we treat it as shape. It doesn't really matter. We treat everything as flat. So that is one kind of a distinction. Okay. So with this, let us try to solve some problems so that you will understand here. So here, a thick steel slab of given dimensions, rho is 7,800 CP, and the conductivities are given, is initially at 300 degrees Celsius and is cooled by water jets impinging on one of its surfaces. The temperature of the water is 25 degrees Celsius and the jets maintain an extremely large, approximately uniform convection coefficient at the surface. Assuming that the surface is maintained at the temperature of the water throughout the cooling, how long will it take for the temperature to reach 50 degrees Celsius at a distance of 25 millimeters from the surface? Okay. So this is a problem. In this problem, we have clearly mentioned that this is a thick steel slab. So it doesn't really matter whether it is steel. See, when this is steel slab, the first thing that comes into our mind is a rectangular object. It doesn't really matter in this case whether it's rectangular or spherical or cylinder because the sizes are huge. And also you see, is there any mention of the size of this steel slab? Any dimension is given in this problem? Can you tell me what dimension do we have in this problem?
No, sir.
There's no dimension. Only dimension you see is some distance of interest. So it means at a distance of 25 millimeters from the surface, what happens that this thing. So overall dimensions of the object is not really given in the problem. So this is the typical nature of a semi-infinite solid or problem in semi-infinite solid. So that's how you can understand or you can figure out whether a particular problem is what. Okay. So let us go to the problem first solving. As always, start with a schematic diagram. We have a hard steel slab. And we have jets impinging on the surface of the steel slab. So jet of cold water of 25 25 degrees Celsius. We are given some dimensions. Density is 7,800. K is 50. Cp is 480. Okay. Now, temperature of water is 25 and the jets maintain an extremely large, approximately uniform convection at the surface. Extremely large, H is very high. You see, this water is at 25 degrees Celsius, which is striking this slab, and this slab's initial temperature is given, not Ti, 300 degrees Celsius. So slab is initially at 300 degrees Celsius. Immediately it is subjected to this high velocity jets, so that the convection coefficient is extremely large and uniform convection coefficient at the surface. Assuming that the surface is maintained at the temperature of the water throughout the cooling, that means this surface, this Ts, this H is so large that temperature of the surface is same as the temperature of water. Ts is 25 degrees Celsius. So this fluid temperature and the surface temperature will be equal when the heat transfer coefficient is extremely large. That's the meaning. Assuming that the surface is maintained at the temperature of the water throughout the cooling, how long will it take for the temperature to reach 50 degrees Celsius at a distance of 25 millimeters? So let's say at a distance of 25 millimeters, what is the temperature? So let us say at this cross section. At this cross section, the question is, what is the temperature? That's the question. So initially, the entire object is at 300 degrees Celsius. Now we started cooling from the surface. So surface is initially at 25 degrees Celsius. So the heat transfer from the inside of the slab will take place to the surface and slowly it will cool down. So this 300 degrees Celsius at this point will reduce to some value. We are asked to find out how long will it take temperature to reach. Oh, temperature is given 50 degrees Celsius. So this temperature is given. The temperature is 50 degrees Celsius at a depth of 25 millimeters. What is the time? So how long will it take for that depth to reach a temperature or to cool down to a temperature of 50 degrees Celsius? From what temperature? Initial 300 degrees Celsius. So that is the problem statement. Okay. Now to solve this problem, now as you see, we cannot calculate the Biot number because we are not given any characteristic dimension. Okay, we are told it's what's the statement used here? A thick slab. So these are some characteristic words. Thick. These words will be thick, large, huge. These are the typical characteristics used in the semi-infinite solid. So there are some pointers in this problem indicating that this object is a semi-infinite object. So here this is a large object. One side only is being cooled with jets of water, and this side doesn't even know what is happening here. It is so large. So that is what is called as a semi-infinite object. Okay. Now we'll try to solve this problem. Now open page number 67. All of you open page number 67 in your data book. In your data book, the first one, you see surface temperature suddenly changed and maintained constant. This is the case for a semi-infinite solid. So for this, you see this is the surface temperature suddenly changed and maintained constant. So initially the surface temperature was at 300 degrees Celsius. With this jet of water at 25, it suddenly changed to 25 degrees Celsius and is maintained at 25 degrees Celsius. So what is happening? This slab is cooling and we have to find how long it takes to cool this depth of 25 millimeters to reach 50 degrees Celsius. So for this, you refer to the data book, page number 67. The first set of equation you have, the equation goes like this: Tx minus T naught divided by Ti minus T naught. Okay. What is T naught? Read in the legend. What is T naught? What is given there?
25.
No, in the legend, what is the description of T naught? What temperature is it?
Surface.
Surface temperature. Okay, so this is the equation available for us to calculate. So we know the temperature Tx. So at a distance x, which is 25 millimeters, the temperature is supposed to be 50 degrees Celsius. That we know. T naught is the surface temperature, this 25 degrees Celsius. Ti is 300 degrees Celsius. So left hand side is completely known. On the right hand side, x is the distance 25 millimeters known to us. Alpha is thermal diffusivity K by rho Cp. So we know K, rho and Cp, so we can calculate. So alpha is known, only unknown is tau. So this can be found out. But you see this ERF is what is a mathematical function. It's called as a full form is error function. So you see here in the data book, the equation for the error function is given 2 divided by root of pi multiplied by z minus z cube by 3 factorial, so on and so forth. Okay. So that is the error function definition. But if you turn to page 68, this equation has been solved and tabulated. So if we know if a given value of z is there, we can find the error function of z. So error function is tabulated, and I don't know why it is called error function, but it's some kind of a mathematical function. Try to find out. Probably there will be an interesting story behind that name error function. Okay. Now let us try to solve this problem. What is alpha? We'll have to first find out alpha. K is 50. Rho is 7,800. Cp is 480. So K by rho Cp. Tell me how much this is. .335 into 10 power minus 4 square meters per second. Okay. Now we'll evaluate this Tx. Tx is minus T naught, surface temperature is 5 divided by initial temperature is 100. Equal to of x is 25 millimeters. Yes. By 10 power x by of alpha is okay. Now you see here what is
So
the
it
left?
will be 10 to power minus 5.
Sorry, what is 10 power minus 5? Oh, 5, no? Okay. Yeah. Okay. Now evaluate the left hand side 0.09. 0 of this value. This value, same thing. You can now we'll have to find the value of tau here. That means the term inside the brackets is something we should know. So if you look at the tables here, you see here, the tables are tabulated like I will show you. But this value 0.09, remember this value. This is the error function you have. Okay. Error function of some parameter w is equal to w. Okay, so what is that w? Error function of something is what we got here is 0.09. So that w is 0.08. That means this 0.09 we get if this term in the brackets is 0.08. Okay, you understand this? Error function of 0.08, if you evaluate, the value will be 0.09. So that is what of 0.08 if you evaluate, it will be 0.09. So the value in the brackets is 0.08, or this term is 0.08. So we'll have to rewrite this. 2.5 multiplied by 10 power minus 5 is the 25 multiplied by 10 power minus 6. Sorry. Multiplied by 10 power minus 3 divided by 2 root of alpha is this is equal to 0.08. So from this evaluate the value of tau. Okay, you will have to square it and then evaluate. So what do you get here? Evaluate and tell me. I want you to calculate, all of you. What happened? Not doing?
Sir, calculating, sir. One eight two 8.7.
1828.7. 0.76 seconds.
Yes, sir.
So this is 30.48 minutes. Okay, so it takes about half an hour for this to cool down, for that 25 millimeter depth to cool down. Okay, now this problem can also be solved using this graph. You also have this graph in your data book. Okay. Do you have it?
Yes, sir.
Temperature distribution in a semi-infinite solid with convection boundary condition. Okay, so in this, see here, h root alpha t by k, h is high, infinite. So this is the curve you need to use for this particular study. Okay, and you know x by 2 root alpha t. So from this you can find out. You find this value, you know this value, both of them should meet somewhere on this one. So you will have to figure out where it is. Okay, try to solve this problem, but you should be able to solve this using both equation and also the chart. So first problem we actually solved it using the equation. We'll take up the second problem. Is this the only question asked here? Assuming that the surface is maintained at the temperature of the water throughout the cooling, how long will it take? Yeah, only one question asked, so that's it. So, coming to the next question, a very thick slab with thermal diffusion.
Sir,
Yes?
in that table, the parameter itself contains tau. So how do we find that?
Okay. Okay, see. The parameter is, the last one is infinity. See that? this is infinity. H is infinity because we are told that H is very high. So this is the curve we should see. So whether T is known or unknown, H is infinity. So we should look at this one. Okay, so we know this value. From here, project this and drop vertical here. Okay, read the value of x divided by 2 root alpha t, and from that try to extract tau. Okay.
So I think this would be useful only if the temperature is asked. I mean,
No.
if we know time, then we can have this plot of the curve, and
Yeah,
we can,
see, we can know that, but here luckily we have not a finite heat transfer coefficient, but infinite heat transfer coefficient. So whatever may be the value of T, this parameter is going to be infinity for us. Is it? So this will be the curve of interest. Do we know this value? T minus Ti divided by T infinity minus Ti. What was this for us?
so it was 0.09.
0.09 or something like 0.1 or close to 0.1 or something like this here. So from here you drop a perpendicular here, and from here you x by 2 root alpha t alpha tau. What is so 0.0909, and from this here it's x by 2 root alpha tau. So somewhere here.
1.25 something.
Yeah. But what we are getting here in our problem, x by 2 root alpha tau is actually 0.08. So we'll have to see how exactly to work out this one. Okay, so there seems to be some difference. No, it's not 0.1, it's 0.01. You see, 0.01 here. Can you look at 0.09? 0.09 is 0.1. So compare here. 0.5060709. Yeah, this one only. But it's coming to 1.1, 1.2, 1.2. But whatever value is 0.08. So I'll tell you how to solve this problem using the
I
chart.
think that is for temperature, when temperature is asked and time is given.
No, temperature is known to us, no?
No, I think this graph can be only be used for this temperature thing.
Temperature distribution, no, that is fine. But in this case, H is infinity. That's why I'm trying to figure out. Or you can also do one thing. The graph I didn't show in the slides, but it is in your data book. You see, turn to page number 70. Page number 70, there's another chart where the location X is known, temperature known, to find the time. Okay.
Yes, sir.
So on that, you see here on the x-axis, which on the x-axis, the temperature difference ratio is 0.09 for us, 0.09, which is close to 0.1. So we'll go by 0.1 and draw a horizontal line from 0.1 to the infinity value, hx by k, infinity. And from there, drop a perpendicular to the x-axis. That reads about 0.08.
Yes, sir.
0.0708 something. Okay, so that is where you can use this. So you have to use the second chart for this particular problem. Okay. So what is helping us here is the infinite value of heat transfer coefficient. But anyway, even if we have a finite value of heat transfer coefficient, we should be able to solve it. We will see that now in this problem. The next problem that we are going to see, we will use this chart to solve this problem. You see here, there is again similar problem, but on about a very thick slab with the thermal diffusivity and the thermal conductivity is initially at a uniform temperature of 325 degrees Celsius. Suddenly, the surface is exposed to a coolant at 15 degrees Celsius, for which the convection heat transfer coefficient is 100. So here you see the heat transfer coefficient is not infinity, it's a finite value. And the surface is exposed to a coolant at 15 degrees. Determine the temperatures at the surface and at a depth of 45 millimeters after 3 minutes have elapsed. Okay. So we are asked for two temperatures after 3 minutes time. So time is given. Time is known to us. The depth is known to us. We have to find the temperatures. Two temperatures, one at the surface and also another temperature at a depth of 45 millimeters. So even in this problem, you are seeing that the overall dimension of this thick slab is not given. So there is no way we can calculate the Biot number. So that's pointed that this is a what we call semi-infinite object. Okay. So let us try to solve this problem again. So this is what is the coolant? Coolant is flowing at 15 degrees. Schematic diagram, again very large slab, and Celsius. There is a coolant flowing. So T infinity is degrees Celsius. H is 100. Fusivity is 5. Yeah, that's, and the K is given. K is K, 20. So we have to find out the surface temperature. T naught is equal to how much, and at a depth of this is at this depth, what is the temperature after a time elapsed of 3 minutes. Okay, so time is 3 minutes. 180 seconds. Okay, so what we do is we'll use the chart. So let's say that this is a semi-infinite object. And then we see at the surface, temperature at surface. We'll try to find this out first. Okay, so we'll use the chart. We'll go by the chart solution. So we know the time, we know the location, we don't know the temperature. So location one is surface, other one is at a depth of 45 millimeters. Okay, now let us take up the surface first. We see, turn to page number 69. Turn to page number 69. You see here, read the chart description. Temperature distribution in a semi-infinite solid with the convection boundary condition. So convection boundary condition value H is given, and x by 2 root tau is equal to 0 indicates the surface. So that means you see here we have in this graph. In this graph we have x by 2 root alpha tau starts from 0 up to, we have it as up to 1.5. And here we have T minus T I divided by T infinity minus T I. And the parameter is H alpha, H root alpha tau by K. Now in the description, we have seen that x divided by 2 root alpha tau is equal to 0 indicates the surface. That means whatever you read on the y-axis at x is equal to 0, this is the surface. So we evaluate the T minus Ti divided by T infinity minus Ti. This is what we need to know. For this H root alpha T by K, we should find out what is H root alpha T. H is 100, alpha is 5.6 multiplied by 10 power minus 6 multiplied by tau is 180 divided by k is 20. So tell me what this value is. Calculate that.
Point 158.
0.158. Okay. So this h root alpha t, this curves, there are curves available from 0.05 up to infinity. So take this value as 0.158. We have a curve for 0.1, we have a curve for 0.3. So somewhere in between will be the curve of 0.158. 0.158. Okay. So, and then you find x divided by root alpha tau. X divided by root alpha tau, since we were interested at the surface initially, this value is equal to, that means we have to read this on the axis. So you read the value on the y-axis here. So that will be somewhere between 0.1 and 0.15. It's close to 0.15, but slightly lesser. So we can say that this t minus divided by t infinity minus ti is equal to 0.14. You can see that this chart, you see this chart, this is not linear actually. This is logarithmic on the y-axis. X-axis it is linear. Y-axis is logarithmic. So basically we use this chart. This x by 2 root alpha t is 0. So this is where we are interested in. And our h root alpha tau by k is 0.158 or 0.16. So this is 0.05, this is 0.1, this is 0.2. So somewhere here, somewhere in between. So depending on how well you read this value from the chart, you will be able to get the or get close to the correct answer. Okay. So once we know this temperature ratio, you can find out the value of T. So T is not known, but initial temperature is 325. Temperature 15 minus 325 equal to 0.1. Find out the value of T. You can calculate the value of T, and it turns out to be about 70. Close to 275 Celsius. So this is the surface temperature. Then you should also find the temperature at a depth of 45 millimeters. 45 millimeters from the surface. So in this case, what we have is we have the temp, we have the location, we have the time, we don't know the temperature. So how to solve this again? Again, go by the same chart in page number 69. Now evaluate x divided by 2 root alpha t with x is equal to 45 millimeters. Now part 2 of this problem. Part B. X is equal to millimeters. Therefore, x by 2 root alpha tau is x is 45 multiplied by 10 power minus 3 divided by 2 root alpha is into 180. So you know the value on the x-axis. Okay. Now you also know You also know h root alpha tau by k, 0.158. This is the same as part A, 0.158. What is this value? This will be 0.708, 0.708. Okay, so 0.708 and 0.158. 0.708, this is 0.5, 0.1, so 0.75, so this one somewhere here, and 0.158. So this is the curve I have to see. And or if you have to do it correctly, 0.5, no, 0.7 is this. 0.5, 0.6, 0.7, 0.8, 0.91. So 0.7 is this. From this, you have to not able to draw the vertical line properly. This one and this one. Oh, not this one. If you root this, this is about this temperature ratio is about 0.04. T minus T I divided by T minus T I is 0.04. So from this you can find the value of T. Okay, so in this way you have to finish this problem. There's one more problem here, similar thing. This is a very commonly used problem, very popular problem, especially in semi-infinite solids and heat transfer. So in cold countries, there is a problem of snowing for during winters for a few months. Let us say it's a 3 months period. Now these pipelines which carry water, if they are exposed to the snow, they will freeze. The water will freeze and the pipes will break. But what happens? What we know that under the Earth's surface, it is still warm. So even if it is snowing on the Earth's surface, the underneath is warm. So we want to know in a period of 3 months time, how long it will, 3 months time, the temperature where the water does not freeze, we should find out the depth. Okay, so that means there is again this is we are talking about Earth, and it doesn't really matter whether we take it as a curve or a flat surface. So we will take it as a flat surface. So we have to find the location at which we have to bury the pipeline so that it doesn't freeze. So at the surface, we are told that the what is this? The temperature is at minus 10 degrees Celsius. This is minus 10 degrees Celsius, and the time is it's a few months, 3 months. You see this 3 months time. 3 months. So how long it will take for this minus 10 degrees Celsius to penetrate or something like that. So assuming an initial uniform temperature of 15 degrees for the ground, determine the minimum burial depth to prevent the water pipes from freezing. That means how long will it take? Initially, the temperature was how much? 15. But because the surface is at minus 10 and it's going to be so for the next 3 months, this minus 10 temperature will actually penetrate downwards and downwards, and we have to make sure that these pipes are buried at such a depth so that it doesn't freeze. That means you have to find out the depth that the temperature remains above 0 degrees Celsius at the end of 3 months time. So what is this depth? So that is the problem. You try to solve that problem on your own, and the answers are there. So you can try to figure out. Okay. So this will be the end of the transient conduction part. So what we have seen is 3 types of transient solids, three types of classifications in transient solids. The first one has got a analytical solution. The second one has got analytical solution, but also chart solution is quite convenient. Third one also has got analytical solution, but still chart solutions are convenient. So depending upon the time availability, the accuracy you need, you either go for chart solutions or analytical solutions. Next class, I will teach you two-dimensional steady state conduction and how to evaluate the temperature distribution using what is called as the numerical methods. We have seen one method, right? What we have seen is the chart method, graphical method using conduction shape factor concept. Now, unrelated to that, we are going to see another method. Okay. So we'll touch upon that in the next class. Now I'll take your attendance. Mrutunidhi,
Present, sir.
Lash,
Present,
and Cherian.
Present, sir.
Dhusudan,
Yes, sir.
Pranav Dilip,
Present, sir. Present, sir.
Pranav.
Siddharth present, sir.
Srivatsan, Mitrayan,
Present, sir.
Kanivel,
Present, sir.
Ant,
Yes, sir.
Milalagan, Niranjan, Vaibhav Karan,
Present, sir.
Present, sir.
Sir, Niranjan present, sir.
Niranjan present, Vaibhav Karan,
Present, sir.
Present, sir.
Pratik Krishna, Praveen,
Praveen, present, sir.
Sinju,
Present, sir.
Yadi,
Sir, present, sir. Present, sir. Chaturvedi present, sir.
okay, Hamza Hassan, Ayush Tripathi,
Present, sir.
Present, Hemant Kumar,
Present, sir.
Pa,
Present, sir.
Molly Singh,
Present, sir.
Vania,
Present, sir.
Sai Rohit,
Present, sir.
Raman,
Present, sir.
Present, sir.
Dipesh,
Present, sir.
Venkat,
Yes, sir.
Kumaran,
Present, sir.
who is that? Sri Kumaran or Sundar Krishna?
Kumaran. Kumaran.
Krishna,
Present, sir.
Kunti,
Present, sir.
Niket,
Present, sir.
Badri Narayanan, Vito,
Sir, chat box.
Present, sir.
Rish Raghav,
Yes, sir.
Rahul,
Present, sir.
Firoz,
Present, sir.
Dhar,
Present, sir.
Karthik,
Vishnu present, sir.
Gauri Shankar, Tishwar,
Motisha present, sir.
Prakash,
Present, sir.
Ja,
Present, sir.
M. Kumar,
Yes, sir.
Pravesh,
Present, sir.
Karan Ajay,
Present, sir.
Benold Simon,
Yes, sir.
Krishna,
Yes, sir.
Venkatesh,
Present, sir.
Anakshaya,
Present, sir.
Dev, Varun,
Present, sir.
Rao, Krishna,
Yes, sir.
Vedant Madhur,
Sir, chat box.
Anand,
Present, sir.
Vani,
Present, sir.
Priya Vasan,
Present, sir.
Priyan, Shankar Narayanan, Anish,
Anish present, sir.
Santosh Raj,
Present, sir.
Keshav Kumar,
Present, sir.
Present, sir.
Kartik Prasanna,
Present, sir.
Sai Kaustubh,
Present, sir.
Varun Ahalyan,
Present, sir.
Sarvesh Krishnan,
Present, sir.
Elsie Femina,
Present, sir.
Present, sir.
Effect,
Present, sir.
Present, sir.
we call the absentees. Srivatsan,
Present, sir.
Tamilalagan,
Present, sir.
Tika Krishna, Hamza Hassan, Sundar Krishna,
Present, sir.
Adri Narayanan, Gauri Shankar, Kiran Dev,
Present, sir.
Kunal Rao, Kalai Priyan, Shankar Narayanan,
Present, sir.
So we'll meet again on Thursday. As I said, I'll teach you how to evaluate temperatures in a two-dimensional steady-state conduction system. It's important, and as I told, it's the concept used in all the computational fluid dynamics softwares. So you will use the processing power of the computer in such cases. Okay, very interesting. So I hope you won't miss that. You can leave the class now.